All right, let's go ahead and get started. First of all, I posted an announcement on Canvas just a little bit ago, but my office hours, which are usually 1:30 to 2:30 on Wednesdays, I have to push those back to 2 to 3. So just this week only, or just today only. So next section we get into, basically the last one in this chapter is, again, like this whole chapter has basically been, now that you have a bunch of different tools for integration, what can you do with them? How can you apply them? And so this last section is about some applications specific to physics and engineering. So those of you who are taking physics 1 right now might see some overlap here. But if you're not, I do want to talk about some of like the kind of the vocab and, measurement systems we'll be using just to kind of get us all on the same page. So most of what we're going to do is based around calculating work. And so basically we're building up to that. So in order to talk about work in a physical setting, the first thing we have to talk about is what a force is. So basically the force is a very, very generic term for any action that, influences the motion of an object. So basically a push or a pull. So right now you're all experiencing the force of gravity, and because you're not falling, there's a force of the floor onto you. You probably heard that called the normal force or the reaction force, depending on who has taught you physics, but basically anything that influences the motion of an object. Displacement, and so similar to distance, but with a very, very key addition here. Basically, what is the difference between distance and displacement? Those of you who are taking physics.
Distance is like the total distance moved, whereas displacement, if you move there and back, you technically didn't move anywhere.
Right. So displacement is not about. It's basically just comparing where you began and where you ended. It has nothing to do with what the journey was like in between. Also, do you know what vector quantities and scalar quantities are? What those two words mean? So displacement is which one of those two? It's actually a vector. So displacement, by definition, you need to have a direction, and we won't always typically mention what the direction is, but when we talk about displacement, we can deal in positives and negatives, which means there's some kind of reference. So that is a vector quantity. Where distance is a vector, distance is a scalar. We won't deal with it too much. We're more interested in displacement before we're going. So work is the product of those two things. If you apply a force to something and it displaces, you have done work on it. It's also, you can look at that as the amount of energy you transfer onto something. So if I drop something, what's not breakable around here? If I drop something, gravity does work on it to displace it, which means now this thing has, after it falls, it has less potential energy because that was the work that was done on it. That's what got transferred. How are we doing with the definitions that kind of setting the stage so far? I think all but a couple of you are engineering majors, so hopefully you're either taking physics or have taken it, even if it's not here at some stage. Newton's second law of motion. What is Newton's second law? Yes, that's the one. There's one very subtle but important thing I'm missing there. So you've probably always seen the F equals ma, right? Why am I putting this thing here?
Sum of all the forces in the system.
Right. Yeah. So it's not just, it's not any one force. It's basically if you add up all the forces acting on something, like right now, you're not accelerating, even though the force of gravity is on you, because there are other forces that are countering that. So the sum of all forces is equal to the mass and acceleration And why am I writing these in so many different ways?
Acceleration is the derivative of velocity with respect to time.
Right. So acceleration is the first derivative of velocity. What's this other weird thing over here?
It's the second derivative of position.
Second derivative of position, or second derivative of displacement over time. But yeah, so we've talked about it a lot, that derivatives and integrals are inverses of each other, so we can talk about them in this way. I wish we didn't, but we're going to talk about two different measurement systems here. Basically, the international system of units. So I assume that when you're doing physics here, you pretty much only deal in SI units. Is that the case? So sometimes you might hear them called the MKS units because all the units are based in meters, kilograms, and seconds. Like there are other units, but they're all kind of cobbled together from those things. We'll also talk about things in imperial units. So force typically measured in pounds or tons or things like that. Displacement measured in feet, and work measured in foot-pounds. Do you see anything missing from the imperial unit side of this? Yeah, I mean, there are imperial units for mass. We don't really use them. When we talk about something, how big something is in one of the three countries that uses these units, it's really about, we just go straight to that force. We go straight to pounds, right? Have you ever heard of the unit, the slug? The slug is like, it's an imperial unit for mass, but like the fact that many of you have never heard of that is kind of my point. We just kind of move past it, kind of do without it in the imperial units. So that is going to come into play with some of our calculations, but we'll get there. So talked about force being that sum of all forces being equal to the product of mass and acceleration. If my acceleration is constant, what else has to be constant? Force is going to be constant as well, right? So if your force is constant, then work is pretty simple to calculate. Which, I mean, the first time you ever talked about work, which might have been in middle school or junior high, it's this product here. The work you do on an object is the product of the force and the displacement. One thing I sort of blew by on that last slide is what units is work measured in? Joules. So that's the SI unit. If I move an object a meter and I use a Newton of force to move it that meter, that's a joule. Or imperial units, we use what? Yeah, there's foot-pounds or pound-feet. There is no like collective term. It's the product foot-pounds. But you probably use Newton meters for certain things, but typically in this context, we use joules. What's the force of gravity in both those systems? Yeah, but how many meters per? Yeah, not so. In SI units, the acceleration of gravity is 9.8 meters per second squared. In imperial, 32 feet per second squared. Anything? How are we doing so far? Even if you're not taking physics here, we okay? Okay. So let's do some things with this. So I got an example here. I'm going to lift a 20-pound weight. I'm going to hoist it 30 feet off the ground, and I want to find the work done there. How can I find that work? What do I know about the force here? Always? Constantly 20 pounds? Yeah. So this weight has a constant. Basically, I don't care what the mass is. We're just going off the pounds, but the force so if this thing weighs 20 pounds, what force do I have to put on it to get it off the ground? 20 pounds. So to move it at all, I got to put 20 pounds of force on it. Do I know the displacement? 30 feet. So from there, can I find the work I did on it? So 20 pounds times 30 feet, which is equal to 600 pound-feet, foot-pounds, whichever one you like better. I hear both, they're equivalent. 600 pound-feet, 600 foot-pounds. How we doing? I don't want to promise you never, but pretty much everything I've seen in this context, whatever measurement system you're in, you just live in. So you might be wary of how things are different from one to the other, but to the best of my memory, I've never had, I don't care about the conversion side of this. Just stay with whatever measurement system whatever is native to the question. So constant force, no calculus, but one thing I want to impress upon y'all is that when we do get more complicated with this, the calculation is still fundamentally work is equal to force times displacement. The way we do those things is going to get more complicated. You know, for example, you've known how to find the area of a rectangle for probably half of your lives now or more. But integrals, even though they're using that concept, it gets a lot more difficult, a lot more involved. So we're going to kind of do the same thing, but basically we're all fundamentally going back to the same product of work being a product of force and displacement. So let's use a variable force. So what the heck is this thing I just showed you here? What do we think this capital F function is a function of? That's my force function. And basically, what am I doing with that force function? I am multiplying it by dx. What does dx represent? That's a small change in displacement. So basically what I'm doing is, I mean, if we have a graph, we can still think about it as rectangles, but what I'm really doing is, all right, for every little value of x between a and b, I'm going to figure out what the force is, and I'm going to move the object a very tiny amount, find that work, and I'll do that over and over and over again until I've swept out the whole interval. So trying to get away from the kind of the graphical paradigm and drawing rectangles, but really the only thing an integral does, I say only, I'm not trying to trivialize it, but really the only thing that an integral does is it accumulates a bunch of really tiny things, adds them all up, and gives you a result. And we can do a lot of things with that, as you've seen: volumes, areas, arc lengths. And now we're finding work, finding physical, mechanical work. So we've seen a constant force. Let's do a variable force. So I have a particle located x feet from the origin, and I have this variable force acting on it. So the force changes as as you get away from the origin, your force changes. I don't know how much work it takes to move it from one place to another. So how can we set that up? So we know that work is equal to the product of force and displacement. But in this case, force varies, right? What do I know about how my force changes? Right, so it's this function, right? Force is a function of my position, where I am. So if that's my force, so we know that it's equal to force times displacement. So can I just multiply this thing by 4? It's a variable force, right? So I have to know what the force is at every single place between 3 and 7. How many values are there between 3 and 7? An infinite, uncountably infinite number of them. So because of that, I have to do an integral. So I'm going to integrate the force function. And what do I have to do with force to get to work? I have to multiply it by displacement. And since this force function is a function of displacement, I'm going to, my dx does the job that I want it to do. So I have force, which is a function of displacement, and I want to multiply that force by a tiny displacement. That'll give me a small little elemental work. So how do I get the full work over the movement that I care about? So the bounds are going to do that for me. I want to integrate from 3 to 7. So the integral from 3 to 7 of what? X squared plus 2x dx. So I'll pause here. What questions do we have about where this integral came from, how we set it up? Or if we're okay with it, can we compute it? How? Take the integral, which is a third x cubed plus what? Plus x squared. Evaluated from 3 to 7. 7 cubed is 343. I'm going off memory, so please correct me. Plus 49 minus. Does this last set of parentheses just cancel out? Oh no, they're adding together. Can someone verify 343 for me? Okay, so 343 over 3 plus 49 minus 18. So we're dealing in physical measurements now, so the burden to keep these things exact is pretty much gone. So let's go ahead and get an approximate number. I got 145 and a third, I believe. 145.3 watts. We should. Should be foot pounds. So look back at the first bullet. So one thing that I'll kind of, so what I believe happens and what a lot of research says happens is that most people, when they look at math problems, they go into math reading mode and they look for equations, they look for numbers. Try to get away from that, because you really do need to know what the units are. Not just you can tack on foot pounds at the end of this question, but there will be implications later for, fundamentally how these problems are solved. So make sure you're attending to what measurement system you're dealing in. So feet and pounds, that means that we're dealing with imperial units, so we need to follow suit. So any questions on that? So how we set up the integral, I believe strongly you can all compute that integral without much help from me. But then in terms of knowing what unit system you're in, how are we doing? Go ahead.
For problems like this on a test, would like the labeling be important? Like
It could be. It could be. That's one of the reasons I'm asking you to be aware of it. If I wrote joules at the end of this, I got the correct number, but by calling it the wrong unit, I'm throwing off the actual value of the thing I found. I think it was NASA, maybe before you were born, but they crashed something because they were either failing to convert feet to meters or the other way around. It's something they were calculating in it. So it didn't end up where it needed to end up, or it ended up where it needed to end up too quickly. All right, so what I'm showing here is a graph of force as a function of position. And I want to find the work here. How can we do that? Why will the area give me what I want?
That's the net change in force over distance or force.
So I'll write down basically we know that work is equal to force times displacement. We have to make that a little more complex for forces that vary. But really, these two things are basically saying the same thing, one in a much more sophisticated way. I want to know what the integral of the force function is over my x interval, which, even though I'm not really asking a question about area, we can think about integrals as dealing with areas. So does that thinking kind of make sense about why the area underneath this graph will give us a work? Okay, so now let's find that area. What is that area? Oh, how'd you get there?
The triangle first.
Okay, so we have a triangle here. So let's split this up into two areas.
Base times height. 2 for that one.
Okay, so let's actually talk about this as integrals as well. If I wanted to set up an integral for that first area, that triangle, what would my bounds be, first of all? 0 to 4. For now, I'll just call it f of 1x dx. Oh, not 0 to 4. What's the other integral? 4 to 8. And for that one, I think I really could simply just say 30 dx, right? Is that fair for the second one? I don't really have a variable force for the second half of this. So I believe this one becomes 120. And this one is, what, 4 times 30 divided by 2? 60 plus 120, or 180 somethings. What are the somethings? Newton meters or joules.
Is that a straight line?
I did, yeah, that's why I just wrote down 30 as the function. If we're being completionist, let's give a function for what f of 1 is. 30 over 4 times x. I know that's not reduced, but I think that gives a good idea of, I mean, that's basically the slope is what I'm writing down at 30 over 4. How are we doing? All right. Is Hooke's law something that is familiar to people? What is Hooke's law? Yeah, so the formula, the kx is, that is like the expression for it, but yeah, basically it's about springs or elastic bands, basically anything that you can deform elastically. So basically anything that can be compressed or extended and will more or less return back to whatever its original form was. So springs, rubber bands. So basically what Hooke's law does is basically assumes that all those things kind of react the same way. There's some constant K, which basically tells you how stiff the spring is. So the larger that value is, the harder it is to compress or extend one of these things. So if it's the shock absorber in your car, it's going to be bigger than if it's the spring you find in like a pin. But really, in many, many ways, and mathematically speaking, they act exactly the same. They're governed by this force here, or by this force. What does the X stand for? That's something I want to be really clear about. The change in position. So that's one thing to be aware of. So X is basically, did I write this down already? Yeah, I did. So basically X represents a displacement from whatever its rest position is. And the reason I want to point this out is that one thing I want to say that X is not, it is not how long the thing is. It's all about whatever the deviation is from what its equilibrium position is. But if we're going to find the work done against, or the work done on things that are elastic, the definition of work we've been going off of has, like, it's irrelevant what the object is. You're still finding the product of force and displacement. So let's do a couple with something elastic. So I have a spring, naturally 10 centimeters long. Then it takes me 40 newtons to stretch it to a length of 15 centimeters. So I want to know how much work it takes to stretch the thing like that. And then we're going to find out how much work it takes to stretch it 5 centimeters further. So how do I find the work done on an object? And let's kind of get away from the constant force flavor of this. But basically, it's this integral. If I have a force function as a function of displacement, and I want to move it through a displacement from A to B, this will give me my work. So how do I talk about the work, or so how do I talk about the force on this kind of object? Yeah, the force is equal to kx, because this is a spring. Anything elastic, we're going to make the assumption that it acts, that you can characterize it exactly by Hooke's law. So force is equal to k times x. One thing I want to point out is, have people seen this before? F of x equals negative kx. So I'm not using the negative, but why is that negative there? Right, basically, whatever deformation you put on something elastic, it wants it. Maybe not the best word to use, but its tendency is to go back to basically go against that, to go back towards its rest position. I really only want to deal in magnitudes, so because of that, I'm going to leave off the negative sign. So because of that, I can fill in some of the things in this integral, kx dx. Do I know the bounds? Is it 10 to 15? So in Hooke's law, what does the x stand for? It stands for displacement from rest, not truly the length. So because of that, I don't think my bounds are 10, 15. It should be 0 to 5. Because I'm going to stretch it from rest to 5 centimeters longer than its rest length. So very important, but like kind of like deceptive and subtle distinction there. So I want to make sure we talk about it as much as we need to. Are we okay with why the bounds here should be 0 and 5 instead of 10 and 15? All right, is this an integral we can do? Is this an integral we should do yet? I mean, I think we could, but I would like to know what that k is. Do I have enough information to figure out what k is? How? What original equation? Sorry. So I know that f of x equals kx, right? If I have a force and I have a displacement, I think I can get k. Do I have a data point like that?
Yes.
What do I have?
40 newtons and
40 newtons equals k times 5 centimeters, which means that k is equal to what? And I'm going to be very clear about units, 8 watts. Newtons per centimeter. Which is totally fine to talk about work or talk about things in distance units that are not meters. We just have to be consistent with it. So our integral now is the integral from 0 to 5 of 8x dx. One thing I want to be clear about here is, so we're saying that x is in centimeters, right? Does that fit with our bounds? 0 and 5? Okay, so I think we're okay. Where do we go from here? How do we feel about doing this integral now? Can we do it? All right, what is it? It's the integral, so 4x squared evaluated from 0 to 5, should we get 4 times 5 squared minus 4 times 0 squared? What's that equal to? 100 watts. Not joules. Newton centimeters. Can we find what it is in joules? Divided by 10. I don't think 10. So if it's 100 Newton centimeters, I would like to get this in terms of joules equivalent to what? Newton meters. So let's do this. Right after I told you all I wouldn't have you convert, but let's do it this one time. Do we agree this is equivalent? A meter is equal to 100 centimeters. So if I do that, I should get a single joule. So really, neither of these is more correct than the other. 100 Newton centimeters and 1 joule or 1 Newton meter, those are equivalent. But yeah, that's the work it takes to stretch the spring from its equilibrium length and then 5 centimeters beyond that. How are we doing? Okay, so the next bullet, the final bullet, how much work is needed to stretch it 5 centimeters further than that? Change my bounds to what? 0 to 10. I think I need to be clear about something. I'm not stretching it from rest to 10 centimeters. Basically, this is just the second stretch. I don't think it's 0 to 5 either. So basically, it's initially stretched 5 centimeters. I want to stretch it 5 more. Would this integral be different than the one I just did? Or in other words, should it take the same amount of work to do this? Or should it be harder? I mean, I'm trying to think of what's a spring you actually try to manipulate by hand. Slinkies are kind of a bad example though, because you can't compress them. They just kind of rest all stacked up, right? But if you've ever tried to, like, I don't know, gotten a hold of like a shock absorber, you can only condense them so much before it just becomes impossible for you. So, and that's what Hooke's law says, the force required to compress these increases the more you do so. So this number should be bigger. First of all, when I do this integral, what's it going to be in terms of? What units am I going to get a work in? Newton centimeters. Can we make some modifications to make it joules? Yeah, we can divide by 100, or the equivalent would be this. I'm going to divide the bounds by 100 from 0.05 to 0.1. Would the 8 change? I don't know, let's do Hooke's law again. We said that 40 newtons equals K times, this would be 0.05 meters, right? So what would that make K? 800 newtons per meter. Am I throwing too many moving parts at us? Let's do this. Let's just let's just stay with what we did, knowing that we have a way to convert this to joules at the end. So integrating from 5 to 10 of 8x dx, the antiderivative will be exactly what it was, 4x squared from 10 to 5, or 5 to 10. So I get 4 times 100 minus 4 times 25. That comes out to be 300 watts. Newton centimeters, or how many joules? 3 joules. So basically, to extend the spring twice as much requires 4 times as much work, essentially. And that is the case when you're doing work on a variable force. Yeah, doubling the distance probably does not mean doubling the work. How we doing? Okay. Right, stole this one from the book. How should we begin? Okay. What's the integral going to look like?
To what?
The integral from 0 to 1
Of some force.
of some force dx. So let's be clear. What's the 0 and 1 are in terms of what? So okay, so 0 feet to 1 foot. That should be. I don't know either. I honestly don't think it matters. So I'll say something a little stronger than that. I know it doesn't matter as long as we don't mix and match units, we're going to be fine. But maybe to get away from dealing with non-integer numbers later, let's deal in inches. So from 0 to 12 inches, this integral, so this work integral, do I know what this will equal? Do I know anything about the force? Right, so this is going to equal 12 foot-pounds, which is equivalent to 144 inch-pounds. So even though these are both the same value, or they're the same measurement, I need to throw this one out. Because we're already talking about the interval in terms of inches. We need to talk about any displacement that shows up here in terms of inches. Do I know anything about that force? KX is about all I can tell you about it. So I know that we have a spring. We're going to assume that those follow Hooke's law. So I know the work required to do this displacement is 144 inch-pounds.
If you were to write it out, it would be 12. Split the 1/2 on the outside, so
What 1/2?
when you do the integration, so the integration is gonna be 1/2 kx squared.
Okay, so that's one thing I wanted to talk about. Are we allowed to do this integral even though we don't know the constant k? What do we know about k? It's a constant, so I can integrate around it basically. So 1/2 kx squared evaluated from 0 to 12 equals 144. So basically I am kind of doing the exact opposite way I did in the last example. I'm using the work to figure out what the spring constant is. So 1/2 of k times 144 equals 144. So k equals 2. 2 inch.
Oh, wait, no,
Are we sure it's not? Oh yeah.
2 pounds.
Maybe we should. I think it is 2 pounds, but let's be clear about why that's the case. So let me redo this calculation, but we'll drop in some of the units here.
2 pounds per inch.
So this 144 is inch pounds, right? When I do this integral, what do I end up getting? So kx is a force, right? That's pounds. Dx is a displacement, right? That's inches. It seems like this is going to have no unit at all.
K is usually in it's
Oh yeah, you're
the
right.
unit for force divided by the unit for
Okay.
displacement.
So k is okay. I'm getting lost here.
Yeah.
So x itself is measured in what? Inches. Dx itself is measured in inches. And this right here has to be measured in pounds per inch. Okay, so I believe it now. So £2 per inch. So that is our spring constant, our stiffness constant. What do we actually want to do here? What are we trying to find out? Right. Why is that? What am I trying to find out?
How much work is needed to stretch it?
How much work is needed to stretch it? Basically, exactly 3/4 as much as I already know about, right? So do we have any predictions for what this work should be? Or is there anything we can say about it before we calculate it? So we know that extending it a full foot was 144 inch-pounds, right? So how much less, we're not sure, but it should be less, right? So are we happy with this integral here? Integral from 0 to 9 of 2x dx. What is the antiderivative of 2x? Squared. That comes out to what? 81 what? Inch-pounds. Does that make sense given what we know and what we know about springs? And just to be really clear, what is 3/4 of 144? What's that? 108. So 3/4 of the work needed to stretch it a foot would be 108 inch-pounds. We're less than that, right? Does that make sense with the way we're talking about work done on the spring? Basically, the hardest extension here comes later. That's what Hooke's law says. Basically, the more you extend it, the harder it, the more force is required to stretch it even further. How we doing? All right. So what else do we have time for? I don't know if we'll have time to finish this one, but let's at least talk about it. So I forgot how much bad art I have to do for this stuff. Let's just get over it. So I have a 200-pound cable hanging off the side of the building. And I want to know how much work it takes to draw, like basically, like say I have a spool here. I'm going to wind that all up. How much work is it going to take for me to get all that cable back onto the top of the building? Is it as simple, and is this case as simple as 200 pounds times 40 feet? Why not?
Because as you lift it up, you're lifting less and less weight each time, so the force you need is changing.
Right. So that is something to keep in mind, is that the force kind of feels like it might be constant here because that cable weighs 40. Well, no, that cable weighs 200 pounds. That is absolutely true. But as I draw it into, as I basically like crank it in, like spool it back onto the top of the building, I'm not bearing all that weight anymore. So even though 200 pounds multiplied by 40 feet would be 8,000 foot-pounds, should I expect my work to be different than this? And if your answer is yes, then which way? Should be less work, right? So I know my displacement is going to be 40 feet. My force is going to be not 200 pounds. It's going to be something that varies. But now we got to figure out a way. Can we describe how that force changes with displacement? So that's as far as I want to take this one here, but basically that's going to be like the game for these kind of things is, you know, like with everything else we've done this chapter, setting up the integrals is typically the more valuable and more difficult thing. So figuring out how that force varies is going to be the trick here, and we'll talk more about that on Friday. Good.
When will the homework for this one be? Before or after the break?
After.
Okay.
Friday this is the last week before break, right?
Yeah.
It'll definitely be after.
Okay.